Hello, everyone. Welcome this afternoon to this second edition of the ING's Data Engineering Meetup of this year. My name is Jessie, and today I'm co-hosting this meetup with my colleague Pulkit. So he's with me on the screen. We really want to welcome you, and it's really nice to see all of you joining us today. For this afternoon, we have three amazing speakers for you. We have Rafael, we have Mark, and we have Valentino, and they have prepared a very interesting story for you to tell. So we really hope that you will enjoy them. One practical thing before we start, if you have any questions for our speakers, you can ask them in the chat, which you will see on the right-hand side of your screen. You can already drop them during the talks, and when the talks are finished, so after every presentation, we'll do a Q&A. So that's a little bit from the practical side. So I would say, without further ado, let's introduce our first speaker, and that's Rafael. Rafael V. Pierre. He's a senior machine learning engineer, and his passion is delivering complex end-to-end machine learning solutions that unlock business value and deliver digital change. He has 13 years of experience in diverse technical areas such as software engineering, system architecture, project management, data science, data engineering, cloud engineering, and machine learning engineering. Rafael has developed his career in multiple global organizations such as HSBC Bank, Vattenfall, Koninklijk Ahold Delhaize, and ABN AMRO. And I'm very proud that he, since December, joined ING in the Customer Dialogue Analytics team. And today he will talk about leveraging Airflow, Kubernetes, automatic speed recognition, and parallel progressing to gain insight over customer phone calls. So that's about introducing Rafael. The floor is yours.
Thanks everyone for joining. Can everyone hear me well? I will take that as a yes. Okay. So the topic today is leveraging Airflow, Kubernetes, automatic speech recognition, and parallel processing to gain insights over customer calls. But before proceeding, just a quick round about myself. As Jesse mentioned, I have around 13 years background, mostly in technology in different areas. I have a background in software engineering, Master of Science degree in Information Studies and Data Science. In my career, I focused mostly in financial markets, but also in some different industries like retail, energy, IoT, and some different businesses. Many different technical roles: software engineer, data engineer, data scientist, machine learning engineer, but also project and product management. And since December, I'm part of ING Customer Dialogue Analytics team. Really happy to be here. And my main interests are systems architecture, cloud architecture, microservices, machine learning engineering best practices, and MLOps. Okay, going to our topic. Before diving deep into the technical details, some business context. So in Customer Dialogue Analytics, one of the hottest topics for us is customer service digitalization, right? And as you might be aware, we have many different types of channels for customer service. And today we're going to focus in two of them. So interactive voice response and phone and video, mostly phone through human agent calls. So for digitalization as a strategy, we are talking about focusing on the digital channels, and digital channels in this case, not only IVR, but also chatbots, email, and chat. The idea here is to focus on these channels and reduce the amount of time that we need to spend with human assistance. By that, when we say that, we're basically saying that we want to increase deflection by reducing human assistance, unless it's totally required. And to achieve that, we need to decrease fallback. And just to contextualize a little bit further, fallback happens whenever it's not possible to get assistance through any of these automated channels. So when you're talking to an IVR and you hear a recording say, okay, sorry, I didn't understand what you said. Please wait while I route you to a human assistant. That's basically a case when you're having a fallback. It's really important to reduce that. But how to increase deflection or how to decrease fallback? These are two things that are closely connected, and we need to tackle both of them. Well, a little bit of a glance about customer calls at ING. ING is one of the biggest banks in Europe and in the world, so you would expect that we have a huge volume of customer calls. So taking the Netherlands as an example, we have around 400K monthly calls to interactive voice response. Out of this total, around 40% end up with a human agent. So as we can imagine, there's a huge resource optimization opportunity. If we're able to decrease these to 20% or even 30%, that's already a huge gain, not only financial, but also operational-wise. But when we talk about fallback and human intervention, we have different reasons for that to happen. It can either be because of complexity and security purposes, for example, when it's a case like credit card fraud. But it could also be that the customers are asking about intents that are still not expected, are still not covered by our flow. So in order to tackle that, it's important to do a qualitative analysis over the full conversations that happen between the customer and the agent at ING. We need to understand what kind of topics are being discussed, but how to do it at scale. Well, a good idea is to leverage automatic speech recognition. And in order to use that, well, when we started talking about this, we already had the transcripts for IVR opening sentences, which means that we already had the text for things that customers were asking in the opening sentences in IVR, but we still didn't have the transcribing engine for full conversations. So this was basically not available at the time. So we said, okay, let's do some market analysis. Let's see what's out there. We have different options in this case. Obviously, cloud providers like Google and Azure and AWS, they provide this as an offering. And for languages like English, for example, they have really good offerings. But we also have some niche providers, some smaller companies, and some of them focus in languages like Dutch and other least popular languages. So we have these two avenues that we explored. And well, you always have a trade-off in terms of complexity, performance, and also privacy. If you want to run anything cloud-based, we need to think about privacy. On the other hand, if we're able to run any kind of solution for that on-premise, in terms of privacy, it's a better solution. But it's always a trade-off between these three topics. So in order to get started with a minimum viable product, we did a bit of market analysis, some scanning in the market. We had a group of runner-ups, and we ended up evaluating the offerings from Google, as you can see here, depicted in this plot. But we also evaluated a smaller company which had a focused offering about related to the Dutch language. And for this MVP, Dutch language was our focus. So what we did was to evaluate multiple different types of metrics. We're going to focus today on this one, which is word error rate. And the idea was to confirm, okay, if we go to more niche players, can we get more performance? And in fact, for this exercise, the conclusion was yes. We were able to find a more tailored engine and what we did was a partnership with this company, so that we could create a really tailored solution for transcribing text in Dutch language, not only for Netherlands but also for Belgium. Right. So this was the first step. This was the winner. But then it came the time to implement some kind of actual MVP for that, technically speaking, right? And the way that we did this, we are depicting here in kind of a high level vision. So basically, it all starts here. The customer makes a call to the IVR, which runs on Twilio. We have an intent detection model for call routing purposes based on dialog flow from Google. This is used for routing the customer to the right answer, or sometimes to the right human agent. When the customer talks to the human agent, after that call has taken place, we also want to do two things. First, to run a more fine-grained intent classification model, also using dialog flow, but to detect the intent that is related to the IVR opening sentence. But not only that, what we did in this case was to download the full conversation from Twilio and run the transcription engine, which is based on a Docker container. So this more about the steps at a glance. If you think about, okay, what are the outputs that we got from this process? Basically, we get a text output. For each and every conversation, we get a JSON file with each and every word, the confidence for prediction of each of the words, duration, time, and of course, which word is being spoken. But then also nice to zoom in a little bit about this step here, and we will do this in the coming slide. So here, from the perspective of this MVP, we are talking about some different components running in the same virtual machine. So first step, of course, we need to download the audio files in this virtual machine. After that, we have a Docker container. And we have different steps that are part of this pipeline. First of them, we need to perform diarization, and diarization is basically segregating the conversation into multiple channels. So you always have two people talking in a conversation. So in this step, we basically separate the audio from the agent from the audio of the caller. After that, we are able to run the transcription. So we run transcription for both channels, and we end up with a text file containing the full conversation, all the words that were spoken by the agent, but also by the client. So this MVP solution, as I said, is based on a virtual machine. As an output, we get a text file, and in terms of scheduling, it's a batch process. So the way that we scheduled this was through a simple cron job, which basically triggered a job based on paper mill to run the steps from a Jupyter notebook. Plain and simple. But what are the challenges with this setup? Well, we have a couple of them. The time required to transcribe each conversation on average is around 6 minutes. So what we ended up doing was running the automatic speech recognition engine over a random sample. It's infeasible. It was infeasible to run over the full sample. And another challenge was that we are talking about sequential processing. Basically, the idea here was to process each of the files one by one, which is good for validating the idea, but not the best in terms of throughput. Here we're not able to talk about task and dependency chaining. So if we want to chain different actions taking place after our transcription pipeline is completed, it is a bit cumbersome in the setup. In terms of fault tolerance and retry mechanism, it also becomes difficult to manage that with a simple setup like that. and other things like, for example, alert and monitoring and credentials management and scale in terms of scalability as well. So after some analysis, we ended up with this list of challenges, and we thought, okay, what would be the target solution to overcome these challenges? Well, one of the first items is, okay, we want to have some degree of dependency chaining, because after we perform the transcriptions, we can run some processes to generate additional insights, or storing them in a database, performing some ELT processes to make it suitable for some analytics workloads and some other kind of steps. In order to increase the throughput, we also wished to run multiple containers, not only one container, but multiple containers in parallel. But then, even if we run multiple containers in parallel, it's also important to have the appropriate monitoring and alerting and some retry mechanism as well. In case of anything fails, we want to automatic retry. We wanted the solution to be fault tolerant as well, and some secondary features, for example, as credentials management, to store the credentials encrypted, and to have some flexibility in terms of scaling, being able to not only vertically but also horizontally scale would be also great. And last but not least, we could do all of these, but if we don't store the data properly in a way that is easy enough to run queries on top of it and generate valuable insights, there will be no point. So we also wanted to have a data warehouse to store this data. Okay, so how do we achieve these? We talked about these requirements, but in terms of a solution, in terms of the design, what we were talking about was basically this. So here we have multiple audio files that we want to process, and we want to spin up multiple containers as we wish. And as these containers are spin up, each of these should process multiple audio files in parallel. This way we can guarantee that we can easily control the throughput by spinning up more containers, so we are performing horizontal scaling. And then each of these containers, once the transcription process is finished, we store the resulting output in a Postgres data warehouse. Right. With this design in mind, we thought, okay, what would be the best tool for the job? Well, it didn't take long for us to realize that we could use two different tools, which could be helpful in this case. And these tools are Apache Airflow and Kubernetes. And the nice thing here is that Apache Airflow as a tool has a really nice integration with Kubernetes, some really nice features, which we're going to explore. We're basically talking, when we merge these two words together, we're talking about a really powerful combination. So some features of this setup are each of the Airflow components run in one or more Kubernetes pods. I won't spend too much time talking about what is Airflow, because I think everyone or most people are aware. But this is really a nice thing. Airflow has different components, task scheduler, a web interface, and the workers. So it becomes really flexible to run this setup in a Kubernetes cluster, because each of them is running a separate pod. And not only that, each of the tasks spins up in its own Kubernetes pod. So that opens up some interesting possibilities as well. We can perform a really dynamic resource allocation if you have multiple different tasks. When you write the DAG, you can define what are the CPU and memory requirements for each of the tasks. If you have one task that is more resource intensive, you can scale up the resources for that task. If you have some other simple ones, you don't need to consume all the cluster resources equally. You can tailor that in a way. And an interesting feature as well is that you can specify target nodes through pod affinity. So basically, you can define which nodes in the cluster are going to be hosting each of the tasks. Let's say, for example, that you want to specify a node which has access to a GPU because you want to train a deep learning model. You can easily do that by using pod affinity when writing your DAG task. And of course, we're talking about Kubernetes pods, which means that the tasks are container-based, and that means that we have easier dependency management. Each of the tasks has an isolated environment. In terms of the architecture, visually, what it means is that, as I mentioned previously, so here we have a Kubernetes cluster. Each of these icons represents a pod. You can have different pods running different Airflow components. In this case, the web server, which is the graphical interface, the scheduler, which basically coordinates the different tasks, a metadata DB, which stores the task schedule and definitions and requirements. And of course, you have the workers, which can be as many pods as you wish. Okay, so we came to the demonstration, which is the most exciting part. Unfortunately, we're not able to do a live demonstration because we would need to have access to the internal network. But what I tried to bring here is basically the capabilities that we are talking about when it comes to implementing parallel processing and how we implemented and how we were able to achieve it. So in this picture, we can see the first version of this pipeline. So we start here with the first task. There is a task to download the audio files, perform the decryption. And the focus here, the most critical task in this case is this one, to transcribe these recordings. And in the beginning, we were performing this, as I mentioned, sequentially, right? So we were thinking, okay, how can we parallelize this in the most flexible manner so that we don't need to change the DAG or perform any kind of code change to increase or reduce the degree of parallelization. So the way we implemented this, so we have different connections that are used for this pipeline. Each of the connections has a purpose. So we have one connection for downloading the audio files, but the most important one in this case is the one that we have related to the container, which is used for the transcription. And what we did here was basically adding an additional parameter for specifying the degree of parallelism. And here, for this example, I've set up 10. The default is 1. If you don't have any value here, it's going to be sequentially. But here we can set up as many degrees of parallelism as we want. And what happens after we change this? Well, after we save these changes, this variable is referenced in the DAG definition. So once this is updated, once Airflow reads the new definitions for this parameter, we implemented a dynamic tag so that whenever there is a change in that parameter, we're going to have a different number of tasks running in parallel for the transcription, which means here that each of these tasks will simply process one of the files, one of the audio files, which is still pending to be transcribed. And as long as there are pending files in our target data source, these tasks will keep running. Once all the processing is finished, then we will reach this state here. And after this, it's mostly downstream tasks. So we have one step for uploading the task metadata, and finally uploading the transcription to the database. And as I mentioned, we model this as an ELT process. So here we basically upload the raw data to our data warehouse, and we have a final step to perform some merging and to transform the data so that it is ready to be queried. All right, so which kind of results did we get? Right from the beginning, we are able to increase this capacity tenfold. It is really straightforward to increase the degree of parallelism here. It depends only on the parameter change and of course on resource availability. So if we push the hardware resources that are available in the cluster, we can push this even further. We can increase this to 20 or 100. Let's say that this sky is pretty much the limit here. In terms of resiliency, we have so far 99% success rate for the pipeline. And this degree of scalability also allows us to expand to other regions. So we have currently projects to expand this pipeline to Belgium and to Spain, and many other regions can follow as well. It becomes really straightforward to add more regions to the scope due to the flexibility. And last but not least, since we're storing this data in a data warehouse with some nice tooling, these unlock some interesting insights and metrics. We're able to calculate what is the silence rate on average for each group of agents. This is a nice measure to compare what is the percentage of silence during the call, because that can directly affect the customer happiness with the service. We can also measure, do some quality analysis and check if agents are adhering to call scripts depending on the different teams. And by analyzing this data, we can also understand if there are new customer needs. If we see that it's common that customers mention new products or some new issues that they're facing in the conversations, we can take some measures in order to improve that. And this more of an initial insight perspective. Of course, there are many more use cases that could be explored. We could perform sentiment analysis over the calls, entity recognition, and many other interesting use cases. Well, with that, we wrap up. I want to thank you. If anyone wants to connect on LinkedIn, feel free. I also write frequently in this blog, MLOps How To. If anyone is interested in machine learning engineering, MLOps, feel free to browse. And I think now we can open for some questions.
Thank you, Rafael. It was a very nice presentation, and we have some questions from the audience. Robert Moline asks, first of all, yes, great insights. Are you able to detect sentiment and intent from the call during the call, or were they always processed afterwards?
Good question. Right now, we are talking about more of a batch processing paradigm, which means that once every day we go there and we perform these, we get these transcriptions. So right now, with this current setup, it's not possible, but it is in our pipeline to get the transcriptions in real time, so that you could generate some insights on the sentiment or some additional insights that could help the agent in real time.
Okay. Then we have another question from Dennis from Felsen. Sorry if I mispronounced your name. Is the source code available? Is it open sourced?
No, for this specific engine, it is developed by a third-party company. But with that said, there are currently some other options in the open source world. Facebook just open sourced wave to vec model. That's really interesting. Has some really interesting figures. And I'm pretty sure there are many other options, but for the case of this one, no, it's not open source.
Okay. And John asks, have these insights and metrics resulted in actual changes in these calls or the performance of these conversations?
Right now, we are in a stage more about exploring these insights, and of course, there will be some effort as well in trying to prioritize which of the insights to tackle first, right? And for that, we depend also on a bit of insight from the business as well. So right now, we are currently working together with our end users to define what to tackle first.
Okay. Then we have another question. How complex is your ETL setup? Meaning how many jobs run and at what frequency?
For this one, currently it's not that complex. For this first version, we are basically talking about one batch process where we do two things. As I showed in the slide, as an output, we get currently the words, so a high level of granularity. What we do is some transformation to aggregate that on the sentence level. But not only that, we also group that depending on the different agent queues. So if I could summarize it, it's basically the ELT that we have right now is basically for aggregating under these two dimensions. But of course, as we improve these and start to have more sophisticated use cases, we'll probably need to have more transformation batch processes.
Okay. Yeah, if someone else or anyone else have any more questions, please reach out to us and we will move on to our next presentation. Thank you, Rafael.
Thanks. It's a pleasure. Yeah. Thank you.
Yes, thanks, Rafael. So our next speaker is Mark Roding. He has a background in computer science and consultancy, and Mark loves to build products. He's passionate about technology, craftsmanship, and building teams. He's a software architect, a polyglot developer, blogger, occasional conference speaker, and an open source committer. He's interested in working with the latest technology in an agile environment and dedicated to delivering scalable, high-quality, distributed, and highly available solutions. He's currently the tech lead of Holmes, which is ING's wholesale banking advanced analytics solution that unlocks the potential of unstructured data. And Mark will today talk about building a streaming insights engine. So Mark, the floor is yours.
Because I'm going to switch to my presenter view, so please let me know if you can hear me. Anyone? Okay, I see a yes from Pulkit, so I'm just going to start then. All right, thank you for the introduction. I'm not going to add anything to that. I think that was a very well done introduction. Maybe to start with what Holmes exactly is. So there was already mentioned that Holmes tries to crack unstructured data. And if you look at our vision strategies that we set up with the team, we basically say that Holmes cracks unstructured data to make our bankers faster and better informed by unleashing the power of collective knowledge. What exactly does that mean? That's a lot of words in one sentence. Well, it's pretty simple. Within ING and any big corporate, there are a lot of unstructured documents. Think of PowerPoints, think of PDF documents, think of Word documents, can be any form of unstructured data, which are often fragmented over different document management systems, and especially in bigger organizations, these tend to be hard to combine, which immediately means that it's difficult for users to find the data if they actually know where to look for. So it's very time-consuming to find the information, and oftentimes the systems that allow you to search for those type of documents only allow you to search on metadata of documents, not on document content itself. If you look at Gartner, who nowadays has a magic quadrant on insight engines. So what is an insight engine? According to Gartner, an insight engine combines search with AI to deliver actionable insights derived from the full spectrum of content and data sources within and external to the enterprise. So simply put, we make data available within documents, and we try to enhance the search capability by applying advanced algorithms and AI capabilities. Going back to our vision, that basically means that we as Holmes, we offer a really simple basic search engine. Think of it as an internal Google to search for document content. And on top of that, we try to enhance the search experience and help users find new information and find information faster by extending this with AI-driven solutions. So Holmes started about 3 years ago as a proof of concept. It was actually my first product that I started working on when I joined WBA about 3 years ago. And Holmes targets, as an initial product, it targets 2,500 employees within ING Wholesale Bank specifically. We currently have 3 different document types that we're ingesting, and we are currently with 250 users, hoping to extend that to the full range of users within 6 months. So if you think about the domain, so what are we actually exactly doing as a product? We've split up the domain into 4 different functional blocks, or 4 different subdomains. The first one would be ingestion, and ingestion has everything to do with retrieving document data plus any metadata that we might want to have into the system from any source system. And if you refer back to the Gartner quote, this could be internal to ING, but this could also be external to ING. So the target user group that we have right now is very much interested in rating reports, which are external reports from, for example, Moody's or S&P. And we're trying to also provide those within the same search engine or same product to basically provide a more complete overview of all the data that could be relevant to the user. Extraction is the concept that we extract any relevant information. So we extract we basically change unstructured data to structured data. I'll get back to that in a bit. Enrichments are any process or any AI-driven solution that we do on top of the extracted information. So if we have converted a document to structured information, what kind of things can we do on top of that data to provide a richer search experience? And one of those, which I'll get to later too, is, for example, classifying which sector a document belongs to, which can make for a really simple filter within Holmes to quickly get the user to specific information on specific sectors, for example. And search, obviously, is all about providing this data to the user either in the front end, but also any search capabilities on top of Elasticsearch or similar tools that we may need to simply have the user search through the content that we have, through the structured data. So diving a little bit into extraction. Extraction is, for us at this moment, a 3-step process. So the first step is optical character recognition. It could be that some documents don't require this step. So if you're thinking about a PDF, for example, they can be searchable. So if you open a PDF, you can sometimes search through the content. Sometimes they're just scanned images, and you will need to use OCR to extract the text from the image, basically. On top of that, we have a process called text extraction, and text extraction is simply extracting all available text in a document. So if a document doesn't require OCR, this is a very simple and very quick step to do. And on top of that, there's a bit more involved process, also a bit more lengthy in terms of processing time. It also a lower success rate, which is table extraction. In table extraction, we're specifically looking for page headers or specific tables within a document, and then looking for specific attributes in that table. And this is information that is obviously very document specific, and is also requires a lot more engineering efforts to produce per document type, basically. So if you think about the functional requirements for us as a product, I mentioned that we started out with, or we are starting out with, 1 user base, but obviously we have the intention to scale this to a bigger audience, hopefully to the entire wholesale banking and hopefully beyond to the entire ING. So we wanted to set out with a few basic rules or requirements that we're going to build a system around, or going to build our product around. And the first one would be that we wanted to scale to a multitude of different documents. Getting an estimate of how many document types that is was quite difficult. Also, per document type, there are different quantities. Some are, for some document types, there are a lot of different documents. Some only come in maybe once or twice a day, or not even. So we wanted to build a system which was able to cope with all these different document types and different scales per document type, basically. As we are in a quite regulated environment as a bank, we wanted to build a system with this in mind from the get-go. So if you look at what we're doing, we don't want to replicate security restrictions which are in source systems. So if you have a specific document type which is in a specific source system that already has its own restrictions on which users can view which documents, that's not something that we want to replicate over and over again for each and every document type that we put into the system. So this was a really important regulation to take into account from the get-go. How are we going to deal with that, basically? We want any change in source system to propagate to our system as soon as possible. Let's imagine that a document gets deleted in the source system. Well, then we obviously need to make sure that it's also deleted from our system, because otherwise we would be showing false content that the user would never be able to get to. Or even worse, let's say that a document is by accident uploaded with the wrong security restrictions. Someone finds out and updates the security restrictions. Well, then we definitely need to get the update as soon as possible. We set out with the principle to get data into our search engine as soon as possible. So if you think back about the two steps that we had, text and table extraction, text extraction is within a second we're able to extract it. Table extraction sometimes can take up to a minute. Also doesn't have the highest success rate. I think we're at about 70% of our main document type in terms of success rate. So we wanted to have a split between those, in which we can say per document type, the minimum required set of data is either only text or maybe text and table, depending on the source type. But as soon as we have the minimum required set of data, we want it to be visible to the user so that we can provide value to our users as soon as possible. And while the system in the background is churning on the enrichments or churning on the table extraction, that data will become available whenever it is available. We don't want to wait for everything to be available before we show it to the user. That's basically the gist. And last but not least, we want our search capabilities and enrichments to, well, they are document specific, but we also wanted them to be, or to have different SLAs. So this refers back to my previous point. Even if we aren't able to run a specific AI model on top of document data that we were able to extract, then having the data in that system as soon as possible, so the text extraction in the system as soon as possible, is still very valuable. So there are different SLAs for different components. In terms of document extraction, that has the highest priority. If something fails there, we need to be on top of that. If one of the enrichments fails for a while, it's less of an impact to the global system. Let's put it that way. And since they are document specific, well, it also was a good guideline for us to think about how we would structure the global architecture. So if we look at some of the architecture techniques, it was already in the title or in the description of the talk today. So I'm going to go through a few of the techniques that we are using. I won't be able to give a really lengthy or really detailed explanation about all of them. They're quite detailed topics on its own, but there's enough information on the internet to find. I add some links in some of the slides, so if you want to know more about one of these, just refer to the presentation. So one of the first that I wanted to start with is the reactive principles. And maybe some of you are already familiar with the Reactive Manifesto, which is a document originating from 2013, created by Lightband, Pivotal, Netflix, and a few other companies. And it basically addresses common problems faced in building modern cloud-driven applications. And on top of that, in 2020, the Reactive Foundation, which is a Linux-based foundation, also released the Reactive Principles, which basically provides guidance and techniques established by people that have been doing reactive programming for a while, mostly since 2013. And it builds on top of the manifesto with practical principles and guidelines that you or your team can follow. So if you think about reactive principles, there are four main principles. To start with the first one, responsiveness. And responsiveness basically means that your system should be able to respond in a timely manner, if it is possible to do so. And this should focus on providing a rapid and consistent response times, for example, but also a consistent quality of service. So you want to give your user the best user experience, obviously, and yeah, especially nowadays when even business users are used to applications like Google or Facebook or Netflix, they have high demands also from business applications. If you think about resiliency, resiliency has to do with responding to failures. So if you have a monolith and something breaks, well, it's simply everything is down, your entire application is down, you can't do a lot except for fix, debug, and get it back online. Resiliency on one hand is about isolation, in the terms of isolating business functionality in different deployables, for example. On the other hand, it's about replication. So if you have a specific component, replication can help with errors or failure related to one of your replicas. The other replicas will still be available to serve your user. It also has to do with delegation of responsibilities. So if you think about elasticity, elasticity has all to do with coping with varying workloads. So if you take into or look back at what I mentioned with different document types, we really were looking when we were building this for a way in which we could scale our architecture to be able to cope with varying workloads over specific document types or parts of the system, basically, that or parts of the workload that our system does. And last but not least, it's mostly message driven in the sense that there are asynchronous boundaries between different components, and that I'll get to why that's important in a bit. So if you think about a big system like what we're building here, it's a system built of smaller components or composed of smaller components, and these principles that are found in the Reactive Manifesto and also the Reactive Foundation, they are really applied to any level of the system. So these principles you can apply at the lowest level, but also on the highest level. So within a specific component, but also across multiple components or your entire system, basically. If you think about the communication pattern, so let's say that you have a set of microservices that need to communicate. The simplest option, of course, is to use some synchronous means of communication, maybe over REST or gRCP. But if you break it down into what kind of communication happens in the system, for us, a system emits events, and think of an event as a fact that happens within a specific system at a specific time. So events are often written in past tense. Simply, they cannot be denied. It happened in a specific part of your system. Then what another service can do, and this is what when I'm talking about the asynchronous boundary, this is where it really shines. A different component, without knowing where a specific event came from, or the other way around, a component that creates an event doesn't need to know who is interested in the data that it produces. A different component can listen to events created somewhere in the system and decide to do its own processing or its own metadata enrichment or anything it actually wants to do with those events. It's free to do whatever it wants. So you can listen to events created elsewhere. Besides that, a service or component can also listen to commands and think of a command as simply a demand to do something. So I want a specific component to ingest a document or run some extraction. I could, as a callee, emit a command to that service to ask it to do something. And last but not least, it can also respond to queries. So since data is segregated over multiple components, you need to figure out a way to get to that data. And oftentimes you can use a query for that. With this communication, what we try to do is we try to avoid direct coupling using REST HTTP calls or gRCP for events. And simply for the reason that it promotes loose coupling. So if I have one service which emits an event, and at this specific time there's only one other service interested in knowing that, then it's quite simple to build that. You create an HTTP connection between A to B, and you're done. But what if you, at a certain point, have another consumer that's interested in the events? Are you then going back to your first service to tell it that it needs to be aware of a second component? And are you then going to duplicate the logic and effort of connecting those two again? This basically tends to get messy really quick. So especially for events, it's quite useful to use asynchronous boundaries using a queuing system like Kafka, RabbitMQ, you can get away with a lot of those solutions. So looking at commands and queries, those do tend to go over REST or gRCP, simply because the responses are so specific to a specific consumer, and you would quickly get into a real overhead of maintaining, if you're using Kafka, for example, maintaining topics, just for all the different type of data responses that you could be dealing with. Luckily, in the system that we've built so far, we still don't have any direct HTTP communication or synchronous communication between services at all. So most of it is still everything is still handled over events, asynchronous events. One good tip is if you're going to do anything in terms of commands or queries with doing REST and gRCP, if you think about the reactive principles again, you want to make sure that if someone, let's say component A, sends an HTTP request to you, component B, you validate the request, you accept the request, and you basically tell it that it was accepted. You won't be processing the actual request on the fly while the request is waiting. You want to be able to offload the fact that you received it and unburden the caller. You accepted it, you stored the fact that you're going to process this, and obviously you need to provide some way or some pattern to your consumer to be able to get the data once it's done processing. So with the domain, when you're building distributed systems, there are different techniques that you can use to discover how you're going to do the split, basically. Everybody has seen so many memes and so many stories about microservices and where they go wrong. And it's often, for me at least, it's often the split between, are you reasoning about technical microservices or are you reasoning about functional microservices? So how does your domain, how does your system relate to what the business actually is? And one really interesting technique to use here to help you guide you into the right direction is using domain-driven design. And domain-driven design was introduced and made popular by Eric Evans in a book he released in 2004. Anyone with a software engineering background will most likely know this blue book because nobody can can read through it entirely and understand what he's talking about. But yet it's a very, very interesting architecture technique. And he basically describes it as the expansion upon an application of the domain concept as it applies to the development of software. So in layman's terms, again, it's a technique focused around modeling your software to what the business domain is about. And this is not something that you as a team of engineers can do by yourself. Engineers often aren't domain experts. So there is a real part of, there's a big part of collaboration involved with domain experts, with the business to get to a system that even they can recognize. And some of the benefits are that it eases communication when you're talking to stakeholders, and because you're simply using the same language when describing a certain functionality or a certain set of features. And it also improves flexibility if applied well. So what are some of the things that you can do to discover your domain, which is the biggest thing that you will need to do when you build such a system? For me, it's always around the business, as I mentioned. So it's basically you're looking to bridge the gap between the business and tech. And one of the techniques you can do is to focus on a ubiquitous language, which is basically speak the same language as your business does. If you refer to a specific process in your application with a specific term, but they don't recognize that term, then again, communication is much more difficult than if you can easily relate to the same concepts using the same language. On top of that, there are nowadays a lot of visual collaboration techniques which you can apply. You can find the link down here. There's a GitHub page which has a lot of the different visualization or collaboration techniques which we tend to use. Especially since we're all remote, it's still easily doable with tools like Miro. This is really nice to do as a group. I must admit that it is still completely different from being in the same room, being able to put up stickies, for example, onto a board. But with Miro, we're getting quite close to what it would normally look like. So the different techniques in these on GitHub, they have a different abstraction level. So at a specific point, some are more interesting or less interesting. I see that I'm running a little bit out of time, so I'm going to quickly skip over. This is one of the the techniques are an evolutionary process, so it's not a linear process. You're going to move between techniques depending on the needs that of the business functionality that you're discussing at a certain point. One of the techniques that we used is event storming, which you can see an example of here, which we did about 6 months ago. So looking at this today, what does it actually look like? Holmes is now built up of 4 different domains, and within those domains we have different services, and those different services, they all communicate through Kafka. And if you zoom into some of those, if you think of extraction was about ingestion is about ingesting data from an external system. And we tend to model every source system with its own component, and only that component is responsible for understanding the system and doing whatever it needs to do to get the data into our system. Here is also a really important point where we segregate the external domain from the internal domain. So any ID generation on the outside is lost, and we basically generate an ID of our own to ensure that we will never have an ID clash, because we simply can't count on external systems to always provide unique identifiers. So extraction, as I mentioned, has an orchestrator principle, and the orchestrator is the component that for us determines which workflow to use per document type. So do we only want to extract text, or do we also want to extract tables, for example? And the orchestrator will be responsible for creating the commands and making sure that those 2 different components, they do their job, and also providing taking care of the workflow of the results that come back in. So did it succeed, did it fail, etc. Enrichment is, as I mentioned, the AI-driven solutions that we do on top of the search or the text, the structured data. And we now have 2 different ones. One side, we have company recommendations. So we try to recommend similar companies based on information that we find in the text, and also sector classification, as I said earlier on. And last but not least, we have our front-end part, which consists of a component that exports all the data to Elasticsearch, and a simple front end plus an API that is available to our users. So if you think about the journey that a document goes through, we basically either get a pull message, or we either pull data from a source system, or we get a message from them over a queue, for example. Our ingestion basically ingests the document and the data. The orchestrator will then trigger on the event that a document was ingested, and it will determine for that document type, what are we exactly going to do? So it could be table or text or both. Then it will, when table extraction, for example, is done, that could be the trigger for sector classification to try to classify the sector based on specific fields that we get out of the tables. On the other hand, the orchestrator is also interested in knowing for a specific document whether table extraction failed or succeeded. Same goes for text extraction. And then there's another part which needs both the data from text and table extraction to recommend a company. This is, again, all event-based, so there is no direct communication. So every part of the domain here shares or creates events that are basically about their domain, and multiple consumers are available to listen to those. And last but not least, we have the exporter, which puts everything in Elasticsearch. So the nice thing about this is that anything here can fail, because our user journey is only about this part. We have a front-end application, there is a search API, which directly talks to Elasticsearch. So our complete processing is completely decoupled from the rest of the application, which is a huge benefit. Same goes for the company recommender. API searches for a document, provides the document as soon as possible to the user. Then we'll try to fetch company recommendations for that specific document. Company recommendation can fail without impacting the user too much. I think I'm going to skip over some of the challenges. So maybe to start with the most important one, distributed communication is hard. So it's a service that doesn't need to know who's interested in data. That's good, right? So it provides loose coupling or promotes loose coupling and high cohesion. Adding additional consumers doesn't impact the producer of the event. There are responsibilities of the caller that are no longer there. Like if you do HTTP calls, you need to do a retry. If it fails, you need to have some sort of backup mechanism. If the one that you're calling is having performance issues, you may need some sort of circuit breakers. Those are all nice benefits, but it also introduces new complexity. So processing complexity is internal to the components instead of with an external component. But on the other hand, it produces additional complexity like retrying failed events. So if I'm listening to events and there's an issue with the data in the topic, for example, or I cannot parse that event for whatever reason, I will need to understand how to deal with that. So I might need to move that message to a dead letter queue or to some other means of storing it so that I can continue processing message that I am capable to process. Other things that you may need to think about is, what if I need to get data from a service? How am I going to get that data? So you may want to have some sort of event logs per service. The second one is all about the domain. So you want to separate, as I mentioned before with the IGs, you want to separate the external from the internal. You define your own domain model and you map any external system to that domain model. And when I talk about domain models, it can be from external to internal, but it can even be that different bounded contexts or different subdomains have a different representation of a document. Every domain in our system knows a document, but they all share, or they all have their own definition of what a document in their context actually means. Another big one to think about is, if you're going to work with events, what data do you put into the events? Are you going to create really big events that have all possible data that you could think of that someone might want to have? Or are you going to trim it down to what you think is essential about a specific event? And do you need to provide a different mechanism for consumers to get additional data from you if they are interested in that? And a last one is that you want to prioritize intent over technical simplicity. So you could run into a case where you will have two events that have exactly the same content. And it may be really tempting to then say, I'm just going to merge these into one single event. But by doing so, you need to look for a name of that event that loses the actual business intent of the event. In the short term, that sounds like a really great idea, but in the long term, you won't be able to properly explain your system anymore. And last but not least, diagnosing and issues is a lot harder. So if you think about a monolith, you have one deployable, you can have one place to look through the logs. It's all simple. There is no asynchronous communication over queues and whatnot. So it's simple, but in a distributed system, it's exponentially harder. If you look back at all the services that we have, if getting to an understanding of where a specific document failed is quite difficult to diagnose. How did a document go through the system? So for us, it's setting up the basic hygiene in terms of monitoring, logging, tracing is essential. You don't want to postpone that to a later stage. If you then take it one step further, you really need to invest in dependency health checking and performance monitoring. So at a specific point, if you segregate by responsibilities, you will have, for example, a front end that calls multiple APIs. So you need to be able to, per API that you're exposing, communicate to the outside world whether it's healthy. What kind of dependencies does that service have? Does it depend on Postgres? Does it depend on Elasticsearch? Are they still healthy? So think about degraded states, unhealthy statuses, and think about how that translates into the user experience that you're going to give to your end user. I'm going to skip over this one for a bit. Cross-cutting concerns last is also, I think, one of the biggest challenges that we now have. So we have 5 services in Scala and 4 in Python, and they almost all need authentication, authorization, Kafka, health checking, database connectivity, reprocessing capabilities, and I can keep going. So at a certain point, you hit a boundary where you have more services than developers, and you need to think about how you can get the infrastructure, basically, so the plumbing, how can we get the plumbing out of those services and into a shared location? And there are concepts like a monorepo that you could use. So this is, for us at least, this is one of the most relevant problems that we currently face. All right, so I guess the gist of the story it would be for me that any architecture comes with pros and cons. There is no right way. This could have probably be 3 single services that communicated over HTTP, would introduce simply a whole set of different problems. What you do tend to see is that with the systems, the type of systems as shown here, the complexity shifts from the application level to the infrastructure level. So all of these common concepts you need to manage on an infrastructure level. You don't want to duplicate over multiple components, basically. Overall, I'm very happy with the flexibility that it gives us and the ability to scale to multiple document types, but also isolate failure and provide a really good user experience. Last but not least, if you're interested in working with me on this product or similar products that we do at WBA, please let me know because we are still hiring.
Okay, thank you, Mark. That was a very nice presentation.
I can't hear you, Pulkit.
Can you hear me now?
Yeah, I can.
Yeah, thank you very much. It was a very nice presentation. Unfortunately, we are out of time, so we will please send any questions that you have to Mark, and then Mark will get back to you. And we will move on to the next speaker. Yeah, thanks, Mark, again.
Thank you.
Yes, Mark, thank you very much. So we have the last speaker of this afternoon. We have Valentino Marano. He holds a master's degree in computer science with a thesis named Algorithms and Tools for Storing and Analyzing the Bitcoin Temporal Graph. Valentino has 5 years of experience in local consultancy firm working on data warehouse projects on Exadata platform, for example, in the retail and the fashion segments. Since 1 year, he joined the ING Italy's data management team, and he has been working on data warehouse decommissioning project aimed to fill the data lake in IPC and dismiss the legacy data warehouse. Valentino, his talk will be about Alfred, an engineered approach to the data loading on data lake. So Valentino, the floor is yours.
Thank you, Jesse. I'm Valentino Marano. I'm 27, a data engineer from Tribe Data Management in Italy. And as Jesse said, I just took last month my second level degree in computer science. I've been working for about 5 years in an Oracle partner firm. And last year I joined ING, and now I'm working on Data Lake. I love technology, obviously, theoretic computer science, but also listening to music, photography, and animals. And today I'm very proud to present you Alfred, a product built from scratch by a few chapters engineers in our tribe, Data Management Italy. We will have a presentation more focused on the engineered approach that gave birth to Alfred. First of all, we will see the main problems and needs that we had to satisfy. Then we will introduce some concepts about Alfred and some features. After that, we will have an overview of Alfred's role in a data lake environment. So we will see a sort of overview of the architecture. And at the end, we will explain some benefits. And we will wrap up all the features and benefits we had and time saving. We will start our story with a famous quote. For those who haven't seen it, it's just Star Wars. So ETLs are typical processes to load data in a data warehouse or data lake environment. And one of the most complex aspects, beside the effective single process, is the synchronization and management of all loadings. Because usually ETL tools like DataStage allow to compose more developments and main processes in a bigger one, but unlikely they will manage the right synchronization, balancing, and checks to decide whether a process can be started or not. For example, we may want to start a process that reads some data after that the process that loads those data has been completed correctly. Or maybe we just want to serialize accesses to some resources without specifying which process must be the first one and which process must be the second one. Usually, dev teams must face those kind of problems and spend much time by taking away from really valuable ETL activities. So if I have to code all the synchronization and process management, I cannot take the right time for performance tuning or maybe to design the code in the right way. We all know that teams are always in a hurry to manage all new developments, reworks, and in this way you can save pressure time. On the other hand, maintenance team needs a tool to easily monitor, prioritize, and interact with the loading flows, even without being expert of ETL tools, as usually happens. Moreover, maintenance team usually notices that machine is executing too many processes at some times and too few processes in other times. In this way, we can just try to have better balancing. We decided to put all this standard stuff and general needs we had in an abstraction layer, Alfred. In this way, developers can focus on their main ETL activity and create units of work in an atomic way. And Alfred will take care and orchestrate processes, execute them in the right moment, basing on priority, constraints, and rules defined by the user. Moreover, it will also take care of standard processes we need by offering specific models, for example, for environment maintenance, statistic gathering, data quality, etc. Alfred is mainly based on database configuration. In this way, any user can change its behavior or reorganize all processes without coding. And usually, ETL tools can be used to build a bigger process by coding and putting many single processes together, but this would require some code to modify the organization. Alfred allows to go beyond that monolithic approach, and in other cases, maybe dev team has to code custom semaphores or synchronization among processes. All the time spent in this kind of activities can be saved and invested in really valuable activities. Alfred orchestrates processes basing on structure and rules defined in its own repository. Let's see some definition before moving on. So we have a queue definition. A queue is just a composition of nodes and tasks organized in a graph way, so it's a sort of graph. For example, in this structure, we can see that Alfred will execute the first task, and after that, he will run its 3 children in parallel, if possible. After the first task, he can start its unique child. And for example, this task can be started just when both its parents have been completed correctly. So far, we talked about task. What is a task? Task for Alfred, it's a unit of work developed by a single atomic process. He knows that he will start that task, it will execute for a while, and at the end, he will complete correctly all with some errors. A task, it's just an abstract container that can be a data stage sequence, a job, a Python script, and so on. Anything that can be run by Alfred. A node is a special task that allows us to ease queue dependencies definition. As a matter of fact, if we want to define dependencies between those 4 fathers and these 3 children, without a node in the middle, we would have to define Cartesian dependencies between each father and each child. Using a node in the middle, we can reduce the number of requested dependencies to have this graph structure. In this slide, we sum up some of the main features. Alfred can start processes when triggered by file arrival or other events, scheduled by specific frequency, or simply invoked by a manual intervention for maintenance team. Alfred can also execute different types of tasks, and if a task ends in error, he will automatically restart the task if needed, or if the user has defined it. In this way, we can be sure that in some cases the task will be executed correctly if the problem is just an infrastructure problem. It can run different kinds of tasks that can be run from native technology. Alfred also takes care of the execution, so he will decide which process must be started in any moment, basing on dependencies defined by user, basing on constant, but also basing on priorities. In this way, he will avoid to overload the machine by limiting the number of current parallel processes, and will try to balance all the processes through the whole day, let's say. He offers also some database reports to help maintenance team to be aware of current status of all loadings. And he sends periodic reports with performance statistics and variety of automatic emails notification. We can also ask Alfred to send emails to different group of people for different events. It's just some configuration. For example, we may want to send a maintenance team email if the queue cannot be started because of some constraint. But for the same queue, we want to send a different kind of email with the business team when the queue will be completed correctly. Moreover, Alfred email utility can be used in custom processes to send emails with attachments with all the benefits of an abstraction layer. We can change addresses, we can change the server SMTP to send emails without coding, but just with easy configurations. Here we can see the architecture of the environment. On the left side, there are the source systems, local and global. In the middle, there is all the data lake environment with the different layers, and Alfred repository lives on this environment. And on the right hand, we can see all the outputs generated from the data lake. So data reports, analysis, local and global consumption, and everything else. In this way, Alfred manages all processes running on data lake, the loading of data produced by source systems, the transformation of data in intermediate layers till the data merge fill up, and also the production of the outputs for other environments, non-data lake. For example, the data consumption, or data reports, etc. This is a solution that organizes end-to-end all the environment loadings. In this slide, we put all the benefits and advantages for both dev and maintenance team exposed so far. So first of all, dev team must not worry about coding or managing process orchestration. This part is completely abstracted by Alfred with a sort of black box approach. The queue structure can be modified very easily because it's just a configuration, so we don't need to code. And it's also possible, for example, to duplicate a queue and simulate test cases. Without Alfred, we had to duplicate the coded main object, let's say, modified and test it, and at the end we had to remove it from all environments. Managing as a configuration can be much more easier and flexible. In this way, all time saved from coding can be used for performance tuning and other valuable activities. Moreover, all Alfred configuration can be easily automated. For example, for almost all standard layers, we prepare the utilities in order to automatically generate configuration with minimal inputs. In this way, all Alfred configuration will be almost free, let's say. On the other hand, we have the maintenance team that has a central cockpit to monitor all flows and will be automatically warned about failures or other problems. Moreover, Alfred will be identifying performance leaks and degradation and will send reports about that. In this way, maintenance team can execute deeper analysis and reorganize processes or the right time to execute a process in order to maximize performances and machine usage. So we will not have death times and too heavy times. And in this way, those reports have also different level of details. Some are very technical, for example, for maintenance team or engineer teams, while other reports are more general with an overview and can be also sent to managers or business people that are not interested in too many details, but just want to know the right status as an overview. Moreover, the process execution follows a specific algorithm to prioritize more important processes and avoid machine overloading. In this way, we can push, let's say, the machine to the maximum level of usage without overloading it and without wasting time. In conclusion, Alfred gives many features to the whole pipeline, but can also be extended based on our needs because it's a custom product, so we built it from scratch, and everything that we need can be added as a new feature on Alfred. We are using it to manage all our data lake processes in our environment, and we keep adding more and more features and improvements since its first release. Alfred is built with native technology and designed with an engineered approach using available tools on data lake environment. So we are not using third-party tools or other stuff. And it's designed by people who care of data. This is the most important thing. So there are almost no limits of what we can do and what we can build. Before leaving the microphone to Jesse, I would really like to thank our chapter leads, Daniele Schiavelli and Luca Scovotto, our IT area lead, Fabio Montoli, our tribe lead, Viviana Nasso, and last but not the least, all engineers from Italian Data Management chapter. And thanks for your attention.
Thank you, Valentino. That was a nice presentation. We have some questions from the audience. Bharat Deep asks, how do you ensure optimized resource utilization across multiple parallel tasks?
Because the management of current parallel tasks is managed by Alfred, so he knows how many tasks are running, how heavy are the different tasks, and we can set different levels of parallelism to avoid to overload the machine. So it can be scaled based on the powerful of the machine, based on the power of the database, and can be used as a solution to manage different environments with different counts of processes, let's say.
Okay, so maybe I will ask a follow-up question. So does it anticipate the volume of the data and adjust accordingly, or does it work based on the number of resources that are being used, or the resource usage?
Sorry?
So can it adjust to the volume that is being processed, the amount of data that is being processed, and depending on the steps in the ETL process, or does it work based on the resources that are being used, the resource usage of the cluster?
It's based on the processes that are running. So the code should be designed to fit to have the maximum benefit. So it must be a sort of atomic process. In this way, the more atomic the process is, the best effort Alfred can give and the best benefit we can have from using Alfred. In this way, we have the best product, let's say, to brought to the end of the pipeline.
Okay. Then we have another question from Dennis. What is or are the interfaces of Alfred? Is this kind of serverless computing service?
Let's say that at the moment we are evaluating a sort of interface for Alfred, so that will not be in this way. Users will need to just in a sort of analysis phase. And at the moment, Alfred has a proper interface, let's say, so we can interact with Alfred based on the native technology of Data Lake.
Okay. And
maybe if you want more details, maybe we can also schedule a specific session to deep dive the topic.
Yeah, I think that is the follow-up question from Dennis, saying where can he find technical documentation, quick start guide, etc. for Alfred, right? So Dennis, please contact Valentino and plan a session. So that will help.
Yeah, sure. Thanks for the question.
Yeah. Any other questions from anyone? Okay. Maybe not now. Then please contact Valentino if you have or if you think of some questions later on. Thank you very much, Valentino. It was a nice presentation.
Thank you.
Yeah. Okay. That was the end of our meetup. So I would like to thank all three amazing gentlemen and their presentations and talks that they delivered today. I hope all of you enjoyed them, and then thank you for joining us and asking questions. If you are interested in data science and if you want to learn more about it, our next data science meetup will take place on 10th of June. So yeah, see you next time.
See you next time. Bye.
Thanks everyone. Bye-bye.